Okay, good morning, quantum enthusiasts, prize pantry enthusiasts. Today, we're going to really dive into, for the first time, this quantum subroutine called rotation estimation, which is probably the most important algorithm or sub-algorithm in all of quantum computing. And it's going to be motivated by what we were doing in the previous couple lectures about Grover's algorithm, Grover's SAT algorithm. And you may remember, and I'll remind you in just a second, that at the end of that, we kind of were in the situation where we were very happy, we solved SAT well, if only we could somehow estimate the fraction of strings that satisfied the circuit that we cared about, or sorry, the and or not code C that we care about. And yeah, so today we're going to see how to do that just as efficiently as we need in order to solve SAT quickly with the quantum algorithm. Okay, so let's recap where we were with Grover's algorithm at the end of last lecture. We have, again, this setup. We have some classical code called C that has n input bits and 1 output bit. And we're thinking of this as like an instance of the SAT problem. So we're really interested in trying to find satisfying strings, meaning strings that when you input them into C, or maybe more precisely, the function that C computes, they output 1. This is a very famous problem in theoretical computer science. And we kind of parameterize this problem by this number p, which is the fraction of all strings which satisfy the function f. Okay, satisfying means makes it output 1. And of course, the bigger p is, the easier this problem should be algorithmically. I mean, if I tell you a 10% fraction of the strings satisfy f, then it's really not a hard problem. Just pick, like, I don't know, 100 strings, and probably you'll find a satisfying one. But p could be really small. In fact, p could be like 1 over 2 to the n if there's only one satisfying string. Could even be 0. Okay, so the bigger the p, the easier it should be. And in fact, that's true for classical algorithms, but we'll also see it's even truer for quantum algorithms. Okay, so in this setup, we imagine forming this quantum subroutine capital R, which was these two reflections, if f then minus, and reflecting across uniform. And this is a pretty simple operation. R, or subroutine R, is like order n plus n operations. So just think of R as like the sort of base unit of Grover's algorithm. And hopefully you remember these pictures. We have this like two-dimensional plane somewhere in space that contains these two vectors, the uniform superposition vector, which we knew how to make ourselves, and this vector goal, which was kind of like the uniform superposition over all the satisfying strings. And we didn't know where that one was, so we tried to like move uniform over to goal so that when we measured, we get a satisfying string. And this R, we saw, rotates the two-dimensional plane containing these two vectors by an angle of theta, where theta is extremely closely related to this fraction p. It's basically this relationship. Theta is like 2 times square root p. Okay, and we don't need to know theta or p or anything to set this up, R. I mean, R just always gets set up like this. And so we saw that, like, the first thing we saw was that if you somehow magically knew p exactly, then you would exactly know theta, either by this relationship or like this is like the literal exact relationship. I mean, this is you can check this is precisely the relationship between theta and p. But this is extremely accurate if p is small, which we usually think of it. So if you somehow precisely knew this mystery angle theta, then, and you also know, by the way, that these are at an angle basically 90 degrees, then you would just do this R, 90 degrees divided by theta times, and it would move uniform to goal, and then you would measure, and you would get a satisfying string, and all would be well. So that was great, and that was like very efficient, and it gave us a square root speed up over classical algorithms, but it relied on this, like, I don't know, not realistic assumption that you somehow magically knew the fraction of strings that satisfy C. And then we ended last time by saying, like, well, you don't need to know it exactly. Let's say you somehow knew P, or basically equivalently theta, like knowing P is knowing theta and vice versa because of this. Let's say you somehow magically knew them to within 1%. Okay, you don't know them exactly, within 1%, one significant figure. That would be good enough. I mean, so you'd like more or less know theta, and you'd still rotate by 90 degrees divided by your estimate of theta, and it would be like a little bit off from 90 degrees, but you'd more or less get to goal, and therefore when you measure, you'd probably get a satisfying string. Okay, so this is what we ended on last time. If you somehow knew p or knew theta to within 1%, then you could still find a satisfying x with high probability with this many calls to r. It's basically proportional to 1 over theta, and theta is like square root of p, so it was like square root of 1 over p. And this is like the hallmark quantum square root speed up over classical computers that maybe the most frequent benefit you see of quantum computers theoretically. I mean, you could compare this with the classical algorithm if you knew, even if you knew p to within, I don't know, well, actually, even if you don't know p, with the classical algorithm, you just start picking random strings, inputting them into C, see if they're satisfying. And if a p fraction of them are satisfying, then after about 1 over p times, you would find a satisfying string. And 1 over p is a large number, remember, because p is small. And this says, okay, under this assumption, with quantum computers, you can find it in square root that many operations, basically. Okay, so this is the dream to get to this setup. But we still have this slightly less magical assumption that you somehow know, let's say, theta to 1%. And basically, eliminating that assumption is the content of today's lecture. We're going to show that you can figure out theta to within 1% with how much work? About this much work, order of this much work, order of square root 1 over p. And therefore, if you put these two things together, it'll be like you have this result, but without any magical pre-knowledge of theta. You just have the desired result that, you know, if you're given some circuit C, or sorry, some and or not code C, you don't need to know anything about it. You'll find a satisfying assignment with about order square root 1 over p work, whatever p happens to be. The algorithm will sort of discover p and use square root 1 over p amount of work. Okay, that's the story. So this brings us to, I mean, this task of trying to estimate theta, or equivalently p, but we'll think about estimating theta, is a task of estimating a rotation angle, and that's the exact subject of this fundamental subroutine called rotation estimation, which we're going to spend a lot of time on. Not just because it's important for this Grover-Sat algorithm, but this is also like the central, like maybe most important subroutine for the quantum factoring algorithm, which will be like the grand finale of this class, basically. And we're going to be like always refining our version of rotation estimation and like tweaking it and making it like better and nicer. So like I don't want to like state things precisely right now because we'll change up later, but this is basically the vague description of the rotation estimation problem. You imagine you get access to some state vector, which I'll call ket start. And you also have access to a quantum subroutine, which I'll call mystery rotation. And you maybe know that like if you were to apply mystery rotation to this vector start, it would like rotate it around some two-dimensional subspace by some mystery angle theta. And your task is to, you know, given this stuff, figure out roughly what theta is. So how does this apply to our Grover algorithm setup? Hopefully it's pretty clear. Ket start is ket uniform. This is the vector that we know how to make ourselves, or state vector we know how to make ourselves, and that's where we start. And this mystery rotation is this quantum subroutine R. This quantum subroutine R, which we know how to make, we don't actually know what it does to like all state vectors in space, but we don't really care. We just know that if you start applying it to uniform, then this vector like rotates around, and we just worry about this two-dimensional plane that the state vector stays in. And theta is, you know, this, and you know, that's our goal in life here, is to estimate theta pretty well, to within 1%. Okay, any questions before we get started? Okay, well, we can also get started with these. Thank you. Okay, great. So before we get started, let's make a small assumption that's not very important, but it'll just make our work a little bit cleaner, which is that for the application of SAT, which, you know, Grover's algorithm is all about, it's okay to assume that P is a little bit small. okay to assume, let's just say that P is at most 1/16. There's a couple of ways to do this, but maybe the simplest one intuitively is, if P is bigger than 1/16, then that's great. I mean, it means, like at least 8% of all strings satisfy 8%? I don't know. Satisfy F. So just pick, I don't know, like 100 strings, and it's very high probability you'll find a satisfying string and be done. So, the only difficulty is when P is small, and really, like, the difficulty is P is like really, really small, like 10 to the minus 10. But we'll just assume it's at most 1/16. Okay, but now when we get to talking about this rotation estimation, it's really better to focus on estimating theta. Like, there is no P in rotation estimation, there's just an angle theta. So we just have to use this relationship to figure out what this tells us about theta. If this were true, I guess it would say that like theta is at most like a half, but this is only accurate if P is really small. So we can just use this exact relationship. And I leave it to you as an exercise in using your calculator to show that P at most 1/16, and this precise relationship between theta and P implies that theta is smaller than 30 degrees. Okay, so this is just it'll be like a little bit simpler for us if we assume in this rotation estimation problem that the angle you're trying to estimate is, I don't know, like between 0 and 30 degrees. Okay, so it will be helpful now to think about the simplest possible setting for this rotation estimation problem. So basically, for the rest of the lecture, we're going to forget about this motivation from Sachs and Grover's algorithm. And we'll come back to it either at the very end of this lecture or at the next lecture, just to put the pieces together. But for now, we're just going to think about, like, because there's a lot of ideas involved in this rotation estimation problem, we're just going to think of like the simplest possible setting for it, which is the case where this mystery rotation subroutine just operates on 1 qubit. So that's not what's going on here. Here, when mystery rotation is R, it's actually like R is operating on like this multi-qubit state, and we don't even exactly know ourselves this two-dimensional plane where everything is happening. We just know one vector in it. But like, let's deal with that later and just worry about the simplest situation where, it's a 1 qubit rotation. That's the simplest case. So let me write the setup here. Simplest rotation estimation setup. So the main thing that makes it simple is this mystery rot is a 1 qubit operation. Okay, so it's like somebody gives you like a black box that does some instruction on 1 qubit, and okay, an instruction on 1 qubit is either a rotation or reflection, and let's say you're promised it's a rotation by some mystery angle theta, and you're trying to figure out theta. And we're going to use this, so we'll assume that theta is at most 30 degrees, let's say less than 30 degrees. And I'm also going to assume theta is at least or bigger than 0 degrees. So also the case where theta is 0 is like a little bit annoying. So eventually I'll remove this assumption, but for now, just assume it's a positive angle. And our goal, I didn't really say the exact meaning of estimate theta here, but I'll say it here. Our goal is to output an estimate which I'll call theta hat. I guess in statistics, it's somewhat common to write a hat to mean your guess at what the unknown parameter is. Estimate theta, output an estimate theta hat, which is within 1%. So I'm going to say this is with relative error 1%, by which I precisely mean that theta hat is between 1.01 theta and 0.99 theta. Okay, that's what we're looking for. And it's called like relative error because like the amount of additive error depends on theta itself. Like this should be within 0.01 theta of theta. So that's our goal for today, to solve this problem. And I'll tell you the theorem we're going to prove, the algorithm. Wow, this is a terrible eraser. It's real bad. Some zombie stuff. Okay, so this is doable. With high probability, with switch to red. Order 1 over theta calls to mystery rot. Okay, and this is without knowing anything about theta in advance. Okay, so this, when I say this, I mean solving this problem. Okay, and as I said, we'll put the pieces together probably next lecture, but assuming we can, port this very simple 1 qubit mystery rotation setup back to the Grover setup, which we will be able to. This 1 over theta many calls, that's like 1 over this many calls. So it's big O of this many calls to R. Okay, and that's desirable because that means that you can put all the pieces together, and without knowing anything about P in advance, you can find a satisfying string X using big O of square root 1 over P work. Okay. Okay, so that's what we're going to work on today, this theorem. And let me say a couple things before we get started. One thing is, indeed, as somebody intuited last time, the algorithm is going to be something like binary search for theta. And in fact, in binary search, you're normally narrowing things down by a factor of 2. And basically, keep that in mind in the sense that don't stress for now about getting this error 1%. We're mostly going to work on nailing down theta to a factor of 2. And that's when we nail theta down to a factor of 2, we'll stick something on at the end that gets that 2 down to factor 2 down to 1%. But you should have in mind that theta is maybe it's 0.005, but maybe it's 0.000000005. And the first step is basically let's figure out how many zeros we got to work with here, roughly what is theta. And then we can get the next few significant digits at the end. Okay.